Next, we're going to look at specific heat, and before I show you an example problem of how we'll work some of these that involve calculations, we need to have some idea of what specific heat is. So specific heat is really just the amount of energy needed to raise the temperature of a certain amount of substance. The specific definition is the amount of energy needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. The units for this look very complicated, but in fact can really help you understand what all of this means. So the units of specific heat are joules per gram degree Celsius. So again, that's red, joules per gram degree Celsius. And let's look at a certain example of this to help us understand what it means. We'll take water, which has a specific heat of 4.186 joules per gram degree Celsius. So suppose I take 1 gram of water. For that 1 gram of water, if I add 4.186 joules of energy, the temperature will go up by 1 degree Celsius. If I add twice that much energy, the temperature will go up by 2 degrees Celsius, etc. In the same way, if I have 2 grams of water, I'll need twice this much energy to raise the temperature by 1 degree Celsius. So this number, this 4.186 joules per gram degree Celsius, really ties together all three of those ideas. The fact that the amount of energy I add will affect the temperature, but it depends on mass as well. And so now we're going to look at this in terms of solving some problems. Hey guys, today we're going to be looking at the specific heat of substances and how we use that in calculations. So here's the problem we're going to look at. How much heat is required to increase the temperature of 37 grams of water by 14 degrees Celsius? The specific heat of water is 4.186 joules per gram degree Celsius. So there's a couple things going on here. First, let's stop and think about what we're asked for. How much heat is required? So how much energy flow is required to increase the temperature of 37 grams of water? So I've got 37 grams of water, and I want the temperature to go up by 14 degrees Celsius, and I want to know how much energy I need to pump into this water to make that happen. Remember, heat is a flow of energy. And the key to this whole thing is this specific heat. So the specific heat of water is 4.186 joules per gram degree Celsius. What this tells us is how much energy we have to add for all the various factors involved. So for every gram of water, to increase the temperature of each gram by 1 degree requires 4.186 joules of energy. So if I've got that 37 grams of water and I want to raise the temperature of each gram of that by 1 degree Celsius, I need 4.186 joules for every gram. Also, for every degree increase in temperature, I need 4.186 joules for each one of those. And there's an equation that we'll see in just a second that will help us figure all that out without having to common sense it too much. So now, problem solving. Just like we always do, we start by writing down what they give us. So, what do they give us? They tell us we have 37 grams of water. I'm going to use H2O for water. And the next thing I want you to do after this is I want you to tell me what that quantity is. So 37 grams, that's a mass. Alright, now let's look for other stuff. They tell us 14 degrees Celsius. That is a temperature. And we know this by looking at the units, because degrees Celsius is always a unit of temperature. Grams are always a unit of mass. So it's important that you know how these units match up to their various quantities. And we're also told the specific heat of water, joules per gram degree Celsius. And this is a specific heat. Again, we know that just by, well, it tells us in the problem. Hopefully you caught that. And also by the units, joules per gram degree Celsius is a specific heat. Just as a side note, you can also see this sometimes given in kilograms degree Celsius. Nothing wrong with that, as long as there's a unit of mass and a unit of temperature in the bottom. Alright, things we want. what are we asked for? We are asked for an amount of heat, and we have an abbreviation for heat that might confuse you. We call heat Q. So that is heat. And now we've got this really handy equation that's going to help us solve for all this. And remember, the next thing we do is always just write down any equation we're going to use to solve this. Our equation in this case, Q equals mc delta T. And let's take a second to go over what all this means. Q is heat, m is mass, C is specific heat. So again, you need to know these. Know that Q is the abbreviation for heat. Know that C is the abbreviation for specific heat. Delta T, that's all one thing. Don't think of this as two separate things in the equation. All of this sticks together as one thing. Delta T just means a change in temperature. That triangle that I'm pronouncing as delta, it's a Greek D essentially, so this Greek letter delta just means the change in. So delta T means the change in temperature. How much do I want the temperature to change by? So in this case, 14 degrees Celsius is how much I want the temperature to change by. Now what I'm going to do is I'm going to use my givens and I'm going to substitute them into this equation. And so I'll go right below where this was, and I'll rewrite the things I don't know. I didn't know Q, so I can't substitute anything in. I do know the mass, though. The mass was 37 grams. So I can write down that number. I don't have to put units with this. I can just use the number. So 37 times the specific heat. The specific heat was 4.186. Times the change in temperature. Well, the change in temperature was 14 degrees. And now we've reached a point where all we have to do is perform the calculations. Brief timeout while I grab a calculator. And we're back with a handy-dandy calculator. Let me try and adjust this where maybe you can actually see it some. So now, all I have to do is solve this, and here's where it gets really neat. Notice in this equation, Q equals all this mess. So once I multiply these out, I'll have Q, which is my heat, which is what I wanted. So once I solve this, I have my answer. So I take 37 times 4.186. Remember, when they're written against each other, that means to multiply them. And so my heat will be 2,168, and I'm going to round this off to the hundreds place. So 2,168.35, and then we have to remember what are the units of heat. Well, they're the same as the units for energy. This is going to be in joules. So the amount of heat required to do this would be 2,168.35 joules.